Section: Introduction. In this section, we discuss how generating intermediate thoughts can help us reason and plan to accomplish tasks effectively. We call this deliberate thinking System 2 reasoning, which involves putting in effortful mental activity, especially when automatic thinking, System 1, might lead to errors. In standard large language models, LLMs, System 1 involves directly producing a response without considering intermediate steps, while System 2 includes methods that generate intermediate tokens before generating a response. Various System 2 techniques have been proposed, such as chain of thought, tree of thoughts, and graph of thoughts, which are shown to provide more accurate results but at a higher computational cost. For humans, transitioning from deliberate, System 2, to automatic, System 1, thinking is known as automaticity. This transition involves moving a skill from conscious effort to subconscious execution, similar to how driving to work becomes automatic after repeated practice. In our research, we explore a method called System 2 distillation for AI models. This technique compiles System 2 thinking into System 1 in an unsupervised manner using unlabeled examples. We apply System 2 methods to examples, measure the prediction quality, and distill consistent results into System 1 without generating intermediate steps. Through experiments with different System 2 LLM approaches and tasks, we demonstrate that our approach can distill System 2 reasoning into System 1 effectively, sometimes even outperforming the System 2 teacher. This distillation process reduces computational costs significantly. We observe successful distillation in tasks involving biased opinions, improving responses in reasoning tasks, and evaluating LLMs. However, complex math reasoning tasks requiring chain of thought are challenging to distill into System 1, similar to how humans struggle with tasks that demand deliberate System 2 reasoning. In the context of humans, System 1 is responsible for quick judgments and recognizing patterns, while System 2 is essential for complex problem-solving and handling abstract symbols. Automaticity in psychology describes tasks performed with little conscious thought, like driving a familiar route. Humans use procedural memory to learn tasks through practice, enabling them to perform them without conscious awareness. The concept of unconscious competence signifies the stage where a skill becomes second nature without requiring conscious thought. Section Summary. In this section, we delve into the concept of System 1 and System 2 reasoning, where System 1 involves automatic thinking and System 2 involves deliberate thinking that requires effortful mental activity. We explore the idea of distilling System 2 reasoning into System 1 for AI models through an unsupervised approach, showing that this process can improve results in various tasks while reducing computational costs. This distillation process mirrors how humans transition skills from deliberate to automatic thinking, akin to driving a familiar route becoming second nature through practice and procedural memory. Section: System 1 and System 2 models. In this section, we discuss System 1 and System 2 models. We define a System 1 model as a neural network that gives a response directly without any intermediate steps. However, it can still compute intermediate representations before providing the final response. These intermediate states are usually represented as vectors and contain distributed knowledge rather than specific decisions, similar to how System 1 reasoning works in humans. Despite this, System 1 models can successfully solve a wide range of tasks without needing intermediate steps. Recent studies have shown that language models, which struggle with complex multi-step computations, can perform these tasks by generating intermediate steps into a scratchpad, using prompts or supervised training. This chain of thought reasoning can be triggered in large language models even with zero-shot prompting or with supervised or few-shot methods. Pre-training these models enables them to incorporate reasoning steps in discrete symbols, such as text, which are present in the training data created by humans. On the other hand, System 2 models output discrete tokens, which are beneficial for making sequential logical reasoning steps correctly. However, if the reasoning is incorrect, it is challenging to recover from an incorrect decision compared to latent vector-based reasoning, which can better model a distribution. Various approaches have been proposed to enable deeper reasoning using large language models by generating intermediate outputs, known as LLM programs. These approaches include sub-question decomposition, self-refinement, self-verification, and different search techniques like tree of thoughts. Additionally, a method has been introduced to perform programming tasks with language models by combining various operations like sampling and re-ranking of outputs, steering the model to behave more like a System 2 model. Moving on to the concept of distillation, typically applied to training a less powerful student model to mimic a powerful teacher model's behavior, we see a shift in our work. Instead of using separate models, we employ the same language model as both teacher and student, applying it differently to incorporate intermediate reasoning. This differs from traditional distillation methods where a larger model's output is distilled into a smaller model. For chain-of-thought reasoning, several distillation approaches have been explored, aiming to mimic the internal thought process of a teacher model in the student model. Our work, however, focuses on improving System 1 models rather than generating internal thoughts. Some exceptions involve distilling intermediate thought tokens into the network layers or gradually removing intermediate steps to enhance performance. In our setup, we consider a single large language model capable of operating in two modes, System 1 and System 2. System 2 models can involve multiple prompts, branching, iteration, and search, generating intermediate results for further processing. In contrast, System 1 models directly produce an output without intermediate steps. Various instantiations of System 2 models exist, such as chain-of-thought prompting, System 2 attention, rephrase and respond, and more sophisticated methods like branch-solve-merge. We will conduct experiments with these methods and explore other System 2 approaches like tree of thoughts and graph of thoughts. Section Summary. In this section, we explore System 1 and System 2 models in the context of neural networks. System 1 models output responses directly without intermediate steps, while System 2 models can generate intermediate tokens through multiple prompts, branching, and iteration before producing a final output. Various approaches like chain-of-thought prompting, System 2 attention, and rephrase and respond utilize different strategies for generating intermediate steps in reasoning tasks, showcasing the versatility and complexity of System 2 models in contrast to the more direct System 1 models. Section. Method. System 2 distillation. In this section, we explore the System 2 distillation method. We find that many System 2 techniques are slower during inference due to multiple prompt calls and generating intermediate tokens. Our goal with System 2 distillation is to transfer all the reasoning from System 2 back to System 1 to enhance the direct outputs from the language model. We assume a scenario where the model can learn from unlabeled inputs, similar to how humans learn procedural memory without supervision. For language tasks, having access to instruction following prompts is common, like in the Wild Chat Interactions dataset. The first step of our method involves generating responses using the System 2 model on unlabeled inputs and using these responses as targets for fine-tuning a System 1 model. However, these responses may vary in quality. To improve the training data quality, we introduce an unsupervised curation step based on consistency criteria. We consider self-consistency of outputs and self-consistency under input perturbation to filter out examples. After this curation step, we obtain a refined dataset with filtered inputs and targets. The final step is supervised fine-tuning of the language model using this distilled training set. We initialize the model from its current state and continue training with the new dataset to obtain a System 1 model with improved performance similar to System 2. In our training and evaluation setup, we use Llama 2-70B chat as the base model and explore various System 2 methods like rephrase and respond, System 2 attention, branch-solve-merge, and chain of thought. For System 1, we perform zero-shot inference using the instruction-tuned base model as a baseline. We present task-specific metrics and the average number of tokens generated per input for each method. We specifically delve into rephrase and respond distillation, a System 2 method where the language model first rephrases the question and then generates a response based on the rephrased question to enhance output quality. By comparing one-step and two-step approaches, we observe that the two-step method significantly boosts performance on challenging reasoning tasks. We focus on tasks like last-letter concatenation and coin flip reasoning to investigate the potential of distilling this System 2 approach. Section Summary. In this section, we introduce the System 2 distillation method, which aims to improve the direct outputs from a language model by distilling reasoning from a more complex System 2 model back into a simpler System 1 model. We utilize in-labeled inputs to train the model without supervision, and through a series of steps including response generation and unsupervised curation, we fine-tune the System 1 model to achieve performance gains similar to the System 2 model. This approach involves supervised fine-tuning of the language model with a distilled training set, resulting in an improved System 1 model that can provide enhanced outputs and performance similar to the original System 2 model. Section: Distillation Data. In this section, we created the System 2 distillation dataset to ensure consistent outputs. We conducted 8 sampling iterations for the last letter task and 8 for each stage of the coin flip task for every input. By applying a majority vote, we determined the final output. For the last letter concatenation task, we focused on symbolic reasoning, where the model had to concatenate the last letters of given words. We built a dataset with 1,200 unique English words, creating 200 samples each for training, validation, and testing. The results showed that the System 2 methods outperformed the baseline System 1 model significantly. When analyzing the coin flip reasoning task, which involves predicting the final face of a coin after a series of flips, we found that the System 2 methods also outperformed the System 1 model. By distilling the System 2 methods back into a System 1 model using our unsupervised technique, we achieved high accuracy without the need for extensive prompt engineering. Our study highlighted the importance of consistency filtering in improving model performance. While prompt engineering can enhance System 1 model performance, it may require additional human effort. In contrast, the distilled System 2 model showed consistent performance across different prompts, indicating that extensive prompt engineering might not be necessary for this model. Section Summary. In this section, we construct the System 2 distillation dataset by leveraging self-consistency of outputs, conducting multiple sampling iterations for different tasks. For the last letter concatenation task, we compile a dataset of English words to train models, achieving significant accuracy improvements with System 2 methods over the baseline System 1 model. By distilling the System 2 model back into a System 1 model using an unsupervised technique, we achieve remarkable accuracy, showcasing the effectiveness of our approach in symbolic reasoning tasks like the coin flip reasoning task. Section: System 2 Attention Distillation. In this section, we introduce System 2 Attention Distillation. We proposed System 2 Attention as a method to help models avoid reasoning errors like relying on biased information or focusing on irrelevant details. It works in 2 stages. First, it modifies the input to remove any unwanted information, such as bias or irrelevant context. Then, it pays attention to this revised input, which is shorter and more focused. Our goal is to see if we can distill this approach into System 1. To test this, we concentrated on the sycophancy eval question answering task, which includes biased information known to impact the performance of language models, LLMs. We used 6,668 examples from sycophancy eval for training and 400 examples for evaluation, with 350 having biased inputs and 50 without bias. For distillation data, we employed Universal Self-Consistency, USC, to choose high-quality targets. We generated 20 versions and used the Llama 70B chat model with a USC prompt to create a self-consistent final answer, which served as the distillation target. The results, shown in a table, indicate the average accuracy over 3 random trials. The baseline LLM, System 1, performed poorly on biased inputs, as expected. However, the System 2 distillation significantly improved accuracy for biased inputs, performing similarly well as the System 2 approach. Notably, there was a notable decrease in the average number of tokens used compared to both the baseline and the model, mainly because biased inputs led the baseline LLM to generate more tokens. We also explored the branch-solve-merge distillation method, which involves three modules: branch, solve, and merge. These modules collaborate to break down a task into parallel subtasks guided by specific prompts. While effective, this method is computationally expensive. We aim to distill its benefits while reducing computational costs. For distillation data, we utilize the Open Assistant dataset V2, OASST2, with Turn 1 and English-only data. We ensured data quality using self-consistency under input perturbations. Evaluation was conducted on the OASST2 valid set and MT bench benchmarks. The OASST2 set served as an in-distribution evaluation set, while MT bench provided an out-of-distribution evaluation. Position bias, where LLMs tend to favor certain positions, was also considered in our evaluation. Section Summary. In this section, we introduce System 2 attention distillation, a method designed to address reasoning pitfalls in models by eliminating biased or irrelevant information from inputs. The approach involves a two-stage inference process where the input is first rewritten to remove undesired content, followed by attending to the revised context. We also explore the effectiveness of branch-solve-merge distillation, a technique that breaks down tasks into parallel subtasks guided by specific prompts, aiming to maintain its benefits while reducing computational costs. Section: OASST2 Evaluation Results. In this section, we present the evaluation results on the OASST2 dataset. The table shows how the chain of thought method enhances performance compared to the baseline LLMs. It improves agreement and reduces inconsistency rates. However, this improvement leads to longer inference times. Our distilled System 2 model performs well with only 4 tokens generated, outperforming other models. Specifically, our distilled model based on Llama 2-70B chat surpasses GPT-40125 preview in human agreement and consistency. Moving on to the MT bench evaluation results, we observe similar trends to OASST2. Both chain of thought and our model enhance performance but require more computational resources. Our distilled model achieves higher human agreement, lower inconsistency rates, and is computationally more efficient. Although it slightly lags behind GPT-40125 preview in some areas, it excels in writing, math, and STEM categories. Analyzing the MT bench results by category, we find that our distilled model shows improved agreement across all categories compared to the base model. While it falls short in reasoning, coding, and extraction compared to GPT-40125 preview, it outperforms in writing, math, and STEM. Chain of thought distillation proves effective in enhancing LLM's reasoning abilities, especially for solving complex math problems. The approach generates intermediate tokens representing steps of reasoning before producing the final answer. We explore 2 variants: few-shot, where multiple examples are provided, and zero-shot, where a step-by-step thinking instruction is included. For distillation data, we use majority voting to produce answers for questions from the training split of GSM-8K. The resulting training set consists of question-answer pairs without intermediate reasoning steps, achieving an accuracy of 56.81% for self-supervised targets. In terms of evaluation, we report accuracy over the GSM-8K test set with different majority voting values. The results show improvements with the chain of thought method, but with longer sequences and increased inference costs. Our System 2 distillation method performs poorly due to the unique reasoning required for the GSM-8K task. This underscores the complexity of distillation methods and the need for further research to determine their optimal application.